Okay, another very interesting and important question from thermal properties of matter. Question is, an indirectly heated filament is radiating maximum energy of wavelength this. So it is also related to, means related to Wien's displacement law, because wavelength is involved. Anywhere where wavelength is involved, it will be it there. You have to call Wien's displacement law. What is the law? Law is basically lambda m into t is equals to constant, right? And constant, what is that value? 2.9 into 10 to the power minus 3. This is the value of Wien's displacement constant in meter Kelvin units. So in CGS, sorry, in SI system, it is the value. Now we need to find out the temperature here at first. So T is equals to 2.9 into 10 to the power minus 3 divided by lambda m, means 2.16 into 10 to the power minus 5. So approximately I am taking 2.9 by 2.16 into 10 to the power 2, right? 10, this much means 290 by 2.16. This is the value of temperature. Now and one interesting thing that is that I have missed the unit centimeter. Okay, means it is my mistake actually. I should take that unit because this value is in meter Kelvin unit. This lambda value is in meter Kelvin unit. So you have to convert this in meter unit also. So 10 to the power minus 2 you have to multiply it with. So 2.9 divided by 2.16 into 10 to the power minus 3 and minus 7, so 10 to the power 4, this much Kelvin. So this will be the temperature of that filament. So a filament is glowing and it is radiating some wavelength. So from that radiating wavelength you will get the temperature of this one. So basically if this one is radiating red color of light, right? This one is radiating red color of light, then you know lambda r is approximately 600 nanometer, right? 600 nanometer. If wavelength is known, then you easily can find out the temperature of that substance, that filament, easily. Means it is very simple. Lambda m into t is equals to constant, which is 2.9 into 10 to the power minus 3 meter Kelvin in CGS, in SI system. Okay, so temperature is known now. Now next part of the question is, find the net amount of heat energy lost per second per unit area. So basically they are asking about the net heat energy per second, which is sigma a t to the power 4, but per not only per second, they are asking a per unit area also, means h by a they are asking, which is sigma t to the power 4, about the radiating energy. Radiating energy means Stefan's law. So sigma means how much? Sigma means 5.67 into 10 to the power minus 8 whole, okay, this one into t to the power 4 means it's to the power 4. So 2.9 by 2.16 into 10 to the power 4 whole to the power 4. I am again not going with the calculation because it will be difficult. Okay, now another thing. Okay, sorry, one thing I have made, I made a mistake. Just a second. See how carefully you have to deal with the, means with each and every formula, each and every numericals of thermal properties of matter. See what in which portion I did a mistake. This value I need to find out. So sigma t to the power 4, but this formula will not be valid for this question. Why? Because there is a temperature in the surrounding. This formula is valid for which? For surrounding temperature equals to 0, when t is the absolute temperature and surrounding temperature is 0, right? At that situation this formula is valid. But when there is a temperature in the surrounding, then formula is simply h is equals to sigma a t to the power 4 minus t naught to the power 4. T naught is the surrounding temperature. So we have to look on to everything, means every value, whatever the values are given in the question. Okay, so sigma a t to the power 4 minus t naught to the power 4. Now if you put, then a will be here at the denominator, h by a, because we need to find out h by a, heat energy lost per second per unit area. So sigma into t to the power 4 minus t naught to the power 4. T naught should be in Kelvin unit, obviously. So sigma is what value? Sigma means 5.67 into 10 to the power minus 8 into t means this much. This value is for t. So 2.9 divided by 2.16 into 10 to the power 4 whole to the power 4 minus, now 13 degree centigrade means how much Kelvin? 13 plus 273, right? What we are getting, the 290, right? 290. So now we have put the value 290 whole to the power 4. I don't know how to calculate. Okay, you can calculate it easily, not easily. Actually, it will be difficult to calculate, not that much easy. But still, one means one favor is against the question, that is 5.67 into 10 to the power minus 8 is here na. Now it is 2.9, it is given na. So we can write down like 290 divided by 2.16 into two zeros I have taken for making 2.9 to 290, and 10 to the power 2 it will be whole square, my whole to the power 4, sorry, whole to the power 4 minus 290 to the power 4. Now you can take 290 to the power 4 as common. So 5.67 into 10 to the power minus 8 into 290 to the power 4 common. 100 by 2.16 whole to the power 4 minus 1. So 100 by 2.16 is approximately, if you take 50, then 50 to the power 4 minus 1, then you can, means it will be somehow easier than directly calculating this to the power 4 minus this to the power 4, right? Slightly easier than that. So this is how you can easily go with this kind of problem. So it is the combination of Wien's displacement law and Stefan law in case of radiation of heat, right? So thermal properties of matter, from thermal properties of matter means all kinds of problems we have discussed related to all the formulas. And if you have any doubt regarding any question, any numerical from anywhere, you can comment in the comment section. I will try to solve them in the next upcoming videos. Okay, so I hope this concept, this question is clear to you. Thank you for watching this video.